Hello everyone. Following our previous lecture on decrease and conquer type algorithms, in this video we will focus on divide and conquer type algorithms. First, it might be a good idea to remember that decrease and conquer, because there might be some confusion between decrease and conquer and divide and conquer. With the decrease and conquer, you start with a problem size n, and you reduce the problem size by some amount. You are left with a single subproblem, and once you solve this single subproblem, you reach the solution of the original problem. So that was decrease and conquer. With the divide and conquer, it is similar, but now instead of having only one subproblem, we will have some number of subproblems. This is my original problem of size n. What I will do is I will create some number of subproblems. And those subproblems, each of them will be of size n divided by b. Okay. And how many such problems do I have? So I have a of them. And what happens is once I have the solution of all of these a subproblems, then I will gather their results and I will find the original answer for the main problem. I thought maybe it will be helpful to sketch a general skeleton of a divide and conquer algorithm. Most of the time, these algorithms are recursive algorithms, so that is why we have a base case test at the beginning, and then we create those subproblems, a number of subproblems. So we divide our main problem into subproblems. And once we have the results from those subproblems, we perform a processing. So I call this the other operations. So this will give us the result. The important point that we should take care, and we'll be using in the upcoming slides, is that so we show all the other operations other than creating the child operations with the fn function. So that is why this is my main recursion. So Tn is the main problem, and the cost of that Tn is equal to a times Tn divided by b. And once you have all the solutions of those subproblems, you have this additional fn operations, and you come to the result. And now we will try to compute the time complexity of divide and conquer type algorithms. It is very important to understand, to digest what we are computing. Okay, so this is the recursion tree we are creating. Okay, so this one is my recursion tree. What happens is once I have the results of those subproblems, I will have fn amount of work, and then I will have the result. So in the second level, how many of children do I have? I have 8 children. And all of these guys, once all the subproblems are solved, so they will require fn divided b amount of work. For this reason, at this level, at the root level, my cost is fn. In the first level, my cost is a times fn divided by b. And in the next level, I will have a square subproblems, each with size fn divided by b square. Okay. As I said, I would like to repeat it again. To understand the divide and conquer type algorithms, it is essential to understand what is going on in this recursion tree. I will keep creating the children until when? Until I reach the leaf. And this leaf is the one where the size of the input reduces to 1. You see, here the problem size is n. Here it is n divided by b. It is n divided b square. And then I will reach some point. It will be n divided b to the power of h. Okay, so h being the height of this tree. Okay. If you solve n divided by b to the h is less than or equal to 1 by following the algebraic manipulations, you will reach that the height of this tree is equal to log n in base b. Okay? Now I know the height. Since I know the height, I would like to compute this cost, Tn. It's very simple. What I will do is I will just sum these values. Okay, fn plus a times fn divided by b plus a squared times fn divided by b squared, and that will go on. So you can write it in this notation, right? And I know that each fn is big theta n to the power of t, a polynomial, an efficient computation, you know. Okay, so for I is equal to 0 to h minus 1, so this is the root level 0, this is level 1, and I will reach to level h minus 1. What will happen is I need to just sum the amount of operations I do at each level. Okay, so and the level is denoted by this I. Okay, if you do it, you will see that, so this is equal to n to the power of d, okay, times for I is equal to 0, starting from root up until the leaves. Please just sum these a divided by b to the power of d raised to power I. Okay, so this is my cost. Now, let's more focus on this one. Once we understand this is my cost, okay, you see that term is the key in solving this summation. First case, a divided by b to the power of d. Okay, and this is the power of I, and for I is equal to 0 to h minus 1. Good. Okay, so what happens if a is less than b to the power of d? That means this fraction will be something less than 1, correct? Okay, since that is less than 1, when you take its powers, it will be smaller and smaller and smaller. And then what will happen, if you are curious about the growth of this cost, what will happen? So this will have no contribution. So this will be some constant, small constant, 1, 2, 3, maybe less than 1. So the total cost of my recursion when a is less than b to the power of d is theta n to the power of d. What else? Second case, what if a is equal to b to the d? Then this fraction will be equal to 1, right? Since this is 1, what will happen here? So this is 1, and this will become h. And to the power of d times h. And what is h? It is log n in base b. So that makes my cost big theta n to the d times log n. So you might be curious where is this b here? Actually, you know, you remember the asymptotic notation. What is this? So n to the d times log bn is equal to n to the power of d times log n divided by log b. So log b, so that is a constant, so no need to worry about it. So that makes n to the d times log n. Okay, so that was the second case. As you can imagine, the third case is when this a is greater than b to the d. Then what happens? This is something greater than 1. Okay, so let's assume, let's name a divided by b to the d as a constant c, and I know that this constant is greater than 1. Then my total cost will be something like that. And luckily, we know how to compute the sum of c to the I from I is equal to 0 to h minus 1. So that is from algebra. And once you do it, so that is equal to, what are the dominant terms? N to the d, right? And c to the h. Okay. If we plug c is equal to a divided by b to the power of d, and if we just say that, okay, h is log n base b coming from here, okay. Again, by following some algebraic manipulations, this will turn to this expression. So this one will eliminate this guy, and you will be left with the final complexity of n to the power of log a base b if a is greater than b to the power of d. Okay. I know that comes a bit complicated, but actually that was necessary to understand what master theorem is telling us. Okay, so here is the master theorem, and actually you already derived the master theorem. You have proved it. Okay. Okay, so once you have a divide and conquer type algorithm such that at each level the problem is split into A subproblems, each with size and divided by B, and if the extra cost you will need to gather the results is theta and to the power of D, then there can be just those 3 cases that you investigated. If it is case 1, this is your solution. If this is case 2, this is your final complexity. And if this is case 3, this is your final complexity. But let's try to understand what it means intuitively. Let's start with the first one. So I start with a problem and I split it into some subproblems, right? And what happens, this will go on. Okay. In the first case, when a is less than b to the power of d, so that means the work will die out. That extra work will become smaller and smaller at each level. So the dominant cost will be your cost at the root. If I draw this as a triangle, I can see that, so this is the amount of work you need to deliver at the root, and this is the amount of work just next to it, and this is the amount of work next to it. Okay, so you see, so this is the total Fn at each level. So what is happening? So this is decreasing. If you are asked about the cost of such a sequence, you know that what is the dominant one? So the dominant is at the root. In other words, you may think of this with an analogy. Okay, so I have some amount of work to be done. What I do is I split it to some smaller ones, and but I have many of them. You can say that A the branching factor is a multiplier, okay, and b to the d, okay, is a divider, okay. So there is some work. You split it into A pieces, okay, and then at each one you have to deliver n divided by b to the power of d. Okay, a times n divided by b to the power of d. So that is n over d multiplied by a divided by b to the d. Okay. In the first case, your multiplier is less than your divider. Okay. So if that is the case, then what will happen? Your work will decrease throughout the levels. So your dominant cost will be the one at the root. What happens in the second case? In the second case, your multiplier and your divisor, they are equal. That means in this triangle, at each level, you are having equal amount of work. Since you are having equal amount of work, it's easy, right? So what will happen? So I need to just multiply this fixed amount of work with the height of this tree, and I know that this height of this tree is log bn, so not important the constant, so that is why my total cost turns out to be n to the d times log n. And the last one is when a is greater than b to the power of d. So that means actually at each step in this recursion tree, at each level, what happens, you multiply the load of your parent by a and divide it by b to the power of d. When a is greater than b to the power of d, that means at each level you are increasing your load. So that is why the dominant load will be at the leaf level, and your total cost will be that amount. Okay. Okay. After discussing the master theorem, actually, we need to have some more examples with the master's theorem. Most probably during the lecture in the class, we will be working on that. But my suggestion is please try to spend some time thinking about the cases. Okay, so what each case means and why you have this complexity. So for the divide and conquer type algorithms, the classical examples are the merge sort and quick sort. So we will be doing these two algorithms as exemplary divide and conquer representatives. Okay. You already studied selection sort, bubble sort, and insertion sort. And we all know that those sorting algorithms all have worst case quadratic time complexity, O(n) square, right? Now we will see merge sort and then the quick sort, and these sorting algorithms, they have the time complexity of n log n. And n log n is the optimal time you can obtain with a comparison-based sorting algorithm. So there is a proof of this fact. Most probably we'll be visiting that proof later in the upcoming videos. But now let's focus on merge sort. So what is the main idea of merge sort? I have an array of elements to sort. I have n elements. What I will do is I will divide this array into two partitions, n over 2 on the left, n over 2 on the right. Instead of sorting n elements, I will focus on sorting the left side and the right side, the elements here and the elements here. At the end, if I have the answer of those partitions, I have a sorted n over 2 elements here, and then I will have sorted n over 2 elements here. But there should be an additional step to reach the final result, right? So I need to match them. I need to merge them, sorry. Okay, so let me show you an example. For instance, we'll be doing this example completely, but just for that part. So I am trying to sort this array. I have split it into two, okay? Somehow I know the answer of the left part and I know the answer of the right part. So sorted left part and sorted right part, and then I will be doing a merge operation. How I can do that? Okay, so let me write it here. H9, 1, 4, 5, and 7. Okay. I know that both of them are sorted, so I will just have two pointers on the left and on the right. I will start from here and I will start from here. Okay. So I will compare them. Whichever smaller, I will write it to the output and advance the corresponding pointer to the next one. Now 2 and 4, 2 is smaller, so goes to the output and the pointer comes here, you see? Okay, and now I have 3 on the left and 4 on the right, so 3 is smaller. Let me send it to the output. Now pointer is on 8, 8 and 4, yes, 4 here. Okay, and now 5 and 8, yes, 5 comes here and 7 is here. 7 and 8, yes, 7 comes here. And I'm done with all the elements on the right side. So what I will do is I will just copy the remaining elements on the left side. So you see I have the sorted array. But the point that I would like to bring your attention is whenever you have two sorted lists, the merge operation of these two sorted lists is a linear operation. You just pass over all these elements here and all these elements here just once, as you have already seen, and then you have the final answer. Okay, so these are the just preliminaries for the merge sort. Let's have a look to the merge sort pseudocode. With the merge sort, you would like to sort this array. You come here, so you don't see a base case here. Actually, base case is already included with the if statement, because if n is equal to 1, what will happen? So these elements will be, these instructions will be skipped and the algorithm will return. Okay, so it says that, okay, so when you start with the complete array, divide it into two. Copy the first half to another array and copy the second half to another array. Okay, and then again, call the same merge sort on the left partition and call the merge sort on the right partition. And this part is our fn function. That is the merge. When you have the answer for the array B and array C, then please merge B and C into A. So this is the gathering operation. That part is the split operations, okay? And with this in mind, let's examine the example. Okay, my initial array is here. It has 8 elements. So following the pseudo-code, okay, so I will just copy the first half, and then I will just make a copy of the second half, okay, and then I will continue on the left side, and then when it finishes, I will continue with the right side. So actually what happens is from here, you come to here, and then from here, you arrive here. And once this is just 1, okay, so what it needs, okay, now I'm done. So everything, this part for the parent is done, left child is done for this parent, and I will call the right child, and now it's done. So once these two guys are done, what I can do is I can do a merge operation. Merge 8 and 3. So this will give me that one. Okay, now I have this part. So that means the left child of this node is already done. So I will focus on the right child. I will come here, and then I will go here, and then this will happen. So since these are just one element, what will happen is I will merge them, and I will have 2 and 9. Once the left child and the right child are already done, so they just return, this one has returned, this one has returned, what will happen? We will call a merge between these two guys, which gives us this sorted subarray. Am I done? No, not yet, because actually I am done with all the elements on the left side, but I will need to do it same processing on the right side, which will bring me up until here. And then once this list and this list, they are ready, I will just merge them, and then I will have the final output. Okay, so this is the merge sort operation. So what is the recursion function? What is the recursion representation for the merge sort? To sort n numbers, I will need to sort n over 2 numbers, but I will have 2 such lists. Whenever they are ready, I will need to call the merge operation. So this is my merge. So this is actually this operation, okay? If you would like to use the master's theorem, then what will happen? So A is equal to 2, B is equal to 2, and D is equal to N is equal to N to the power of 1. So D is equal to 1. So that means 2 is equal to 2 to the power of 1, and that makes it case 2. With the case 2, I know that the cost of the complete algorithm is n to the power of d times log n, since d is equal to 1. That makes n log n. N log n is the cost of merge sort, and that is an optimal sorting cost. Actually, without using the master theorem, it is not that much difficult to see why it is n log n. Honestly speaking, maybe this 2 shape makes it a little bit complicated. So what I suggest you is not to consider this part. Okay, so not consider this part. Okay, so you start here, and you have n elements here, then you have n over 2 elements here, you have n over 4 elements here, so you have n over 8 elements here. So your recursion, your tree, keeps growing until you reach a leaf node of size 1. And when that happens, what is the height of your tree? That is log n, right? Log n. It's not difficult to see that. Okay, so log n. And what is the amount of work that I deliver at each step? When I would like to come to the final answer, what I should do is I should merge a list of n over 2 elements with another list of n over 2 elements, which will cost me at most n comparisons, right? So n over 2 here and n over 2 here. I have my pointer here, so this will be scanning the left side, that will be scanning the right side. So in total, the total number of comparisons will be n, right? So I need n comparisons at this node. Similarly, I will need n over 2 here, n over 2 here. And then at this level, again, n over 2 plus n over 2, I will need n comparisons. And comparisons on the root and comparisons on the children of the root. And then if you keep going that, you will see at each level, n over 4, n over 4, n over 4, n over 4, you have always a load of n comparisons. So that is why my total number of comparisons is bounded by n times log n. Okay. And this is my final complexity. Okay, what else I would like to see you here? Oh, yes. So we have a couple of questions and words here. First of all, what is a stable sort? Let me give you an example. I have 2, 3, 5, and 3. Okay, so let's say this is my array. And then you sorted this array 2, 3, 3, and 5. You see there are 2, 3 values here, right? So when you see this 3, is it the first one or the second one, right? Because you don't know. Stable sort means if there are equal elements in the input sequence, then their order of appearance on the sorted sequence is exactly the same as their order of appearance in the input sequence. So that means this 3 is this one, since that appears before, and this 3 is the second 3. Okay, so that's called stable. Okay, and stable sorting is something important in practical application, so it is an advantage. And merge sort, yes, by taking care of this during the merge operation, you can make the merge sort a stable sort. On the other hand, what is an in-place algorithm? Particularly for the sorting algorithms, in place means I will not need an extra space. Whatever I do, I will do it on the input array, which is not the case for the merge sort, because you see, you copy the left partition and right partition to separate arrays. So that means in terms of the space complexity, you are using more space. How much more? Actually, it is around 2n. Okay, so if you have an array of size n, then the extra amount of space that you will need at some time will be around 2n. So we are using some extra space with the merge sort, and merge sort is not an in-place algorithm, but it is a stable sorting algorithm. The implementation of merge sort in this example, so it is a recursive version, and that starts with all the elements, splits it until the leaf contains just one node, and then goes back. Okay, so this is, as you already know, is a top-down approach. You start with the complete problem, you go down until you get the problem size 1, and then you again climb back to the top. The other way, whenever the array is given, I may assume I have all these elements as elements of just one element lists, okay? And then I can build this merge sort tree, not from top down, but from bottom up. And this bottom up usually results in an iterative implementation. You may check this or try yourself for this bottom up implementation. Merge sort is the de facto standard when you would like to sort huge volumes that do not fit into the main memory. We call them the external memory sorting, which we will not be covering in this introductory course. However, moral of the story is, with the merge sort, what we do, we split the input sequence into two partitions, right? Because we choose B is equal to 2. What happens if I split it, let me say, 3 partitions or 4 partitions? Then I will be building not a binary tree, a ternary tree, or some n-ary tree. And this is actually very much used in the external memory sorting, but we will not be covering that here now. I think that is all I can say about the merge sort. And the second sorting algorithm, which is again a classical example of divide and conquer, is the quick sort. Merge sort was invented in mid-40s, 45, I guess, with von Neumann. So at that time, even the programmable computer concept was a top-level secret at the Bletchley Park. So merge sort is older than the modern computing devices, we can say that. On the other hand, quick sort appeared invented in the early 60s. As far as I remember, in 59, Tony Hoare invented the algorithm, but the publication is 61. Okay. Why I am telling you this story? Quick sort is invented later than merge sort. When quick sort is invented, there was already an analog and sorting algorithm, merge sort. However, quick sort became very popular and implemented in nearly all programming languages, in many libraries. And I want you to think about it, why that happened. Maybe we can discuss it after visiting the quick sort algorithm. Okay, so the difference between the quick sort and merge sort is that with the merge sort, whenever you are given an array, you split this array into two according to the position of the elements. So you just draw a line here and you say that all the elements here, so you are the left partition and all the elements here, you are the right partition. On the other hand, what quick sort does is, whenever you have this array, it does not simply make it as the merge sort, it chooses a pivot element. And this pivot element, in the original writing, it is the first element of the array. So once you have this pivot element, what you do is you just pass over this array, and whenever you encounter a value that is less than your pivot, so that goes to left, okay? Whenever you see something greater than your pivot, so that goes to right. So after some time, so the smaller ones will make the left partition and the greater ones will make the right partition. In other words, you have already detected the correct position of your pivotal elements. This is the quick sort idea. Okay. You see. So let's have a look to the pseudocode. It's very, very, very simple. Again, That's a recursive one. So what do? We have the input array, and we choose a pivot element and run a partition. So this is actually your fn function. Okay, that's the partitioning. And then once you have this partitioning, just send the left part to quicksort and right part to quicksort again. And then the same thing will happen. But the point here is how I will make this partitioning. To make it simple, I would like to start with the LaMuto partition. First, with the LaMuto partitioning, you have the element. So this is the leftmost element chosen as the pivot, right? So this is your pivot element. And what you do is you start from this position and just visit all the remaining guys one by one, compare all of them with the value of that pivot. So if they are less than this pivot, so you just move your pointer. So that's the S pointer starting from here. So you move your pointer towards here, okay? And swap the position, swap the element that you see there with the AS, that position with the element you are visiting during that time. Okay, so as an example, so if it is 2, let's say 5, 2, 1, 3, 6, 7 something, so my pivot element is equal to 5, right? So I just copy 5 to a temporary position, and then I set my S is equal to here, okay? And now I start with I pointing here. So I is equal to 2 and S is equal to 5. AI is less than AS, so what will happen? So 2 will be moved here and 5 will be here. And then you will be doing the same thing again and again. So at the end, what will happen? So 2, 1, 3, 5, 6, 7 will appear, okay? So you will make this the left partition and you will make this the right partition. So this is the basic partitioning algorithm. But actually, the inventors of the quicksort, so they make use of another partitioning that we will see on the next slide. Okay, so this is a bit more complicated, but the good thing is everything happens in place. So you will not be in need of some extra positions. This is a bit more complicated, as I said, so I suggest you to study this pseudocode by your own, slowly, and doing everything with pen and paper. Okay, so, but I will try to explain. So this is the partitioning. Again, let me repeat. There is nothing different. So quicksort, the original quicksort algorithm, it is not changing, okay? Again, I am using that quicksort algorithm, but for this partitioning, instead of using this LaMuto partitioning, we will be using another one. We will be using the Juarez partition, okay? How it goes, again, you say that my pivotal element will be here. Okay, so P is equal to leftmost element. I have saved the value of the leftmost element in P. Okay, I'll be maintaining 2 pointers. The first one is I and the second one is J. Okay, so I is pointing to the leftmost position and J is pointing to the rightmost position. Actually, initially it is rightmost plus 1. But that is because I will start from the left and I will be looking for a position that is greater than or equal to P. So I will come to a place such that all the elements are less than or equal to my pivot, but this one, it is greater than or equal. Okay. And I will do the same from the right side. I will come from here, and now I will stop at a position such that the value is less than. When we see these two things happen, what we do, we just swap the values. So this one comes here and this one comes here. And we again continue advancing the pointer I from left to right and J from right to left until they cross each other. Okay, so when they cross each other, it is this case, what I should do is I should do the last swap operation. And after this one, I will be just moving this element. I'll be just swapping AL with the AJ. So whatever I have on the AL, so it will be swapped with the AJ. Best understood with an example. So let's try to focus on this one. Okay. So pivot is 5. Okay. I is here. Is it possible? One moment, please. I will try to make it bigger. Okay. Better. So this is my pivot element. This is I and this is J. Okay. I will keep going until I hits a position greater than 5 and J hits a position less than 5. You see, here I points to 9 and J points to 4. Whenever I hit such a situation, I need to swap the values. So 4 comes here and 9 comes here. So when 4 is here and 9 is here, we continue. Again, I is looking for the value that is greater than 5, which is 8, and J is looking for a value less than 5, so that is 2. You swap them, so that becomes 2, that becomes 8. And you keep doing that. But what happens? So once you do it, you see that so J becomes less than I. Okay. So once J becomes less than I, what we need to do is we need to just make the swap 2 with 5. Okay, so 5 is here and 2 is here. What happened? Actually, on this input array, we have just moved all the elements that are less than 5 to the left partition and all the elements that are greater than 5 to the right partition. Please take care, give attention that at the end of this step, 5 is its correct position. So pivot element moves to its correct position after this pass. Now I will do the same on the left side, and then I will do the same on the right side. Okay. Let me make this a little bit smaller to show you the whole picture now. If we look to the whole operation, so you start here, and at that position, you have these guys here and you have these guys here. You will continue with this part and you will have this one, okay, and then you will have this one. It is that part, okay, and you will have 3 and 4, so it's this one and this one. So you will be done, and then you will be repeating the same thing on the right side. So moral of the story, I will repeat it again. You are given the array, you choose the pivot element, and all the elements that are less than this pivot goes to left. Pivot is its incorrect position, and all the elements greater than pivot, they go to right. You choose the pivot elements, right? And you do the same thing here. Okay, so this one is this, and then you do the same thing here. Again, pivot is in the correct position. And you keep doing this again until this list size, the elements, the number of elements in a list reaches to 1. Okay, so because when it is 1, so you cannot split anymore. So you stop the recursion and you go to, you return the execution to your parent. So that is the way the quicksort algorithm runs. Okay, so now let's return back to our initial question. So what is the difference between the merge sort and the quicksort? Merge sort, it is not a stable sort, right? So you don't know if the original order of appearance between the equal elements are preserved at the output. But with quicksort, actually you are sure about that. The original order of appearance is preserved at the output. So that is an advantage of quicksort. What else? With the quicksort, you do not need to maintain extra space. With the merge sort, when you split the sequence into 2 partitions, you need to save each partition in separate arrays for the health of recursion in your tree. What with the quicksort, you don't need this. You see, everything here happens on the array with those swap functions. There might be a question, can't I make the merge sort an in-place algorithm? So there are works on making merge sort an in-place algorithm, but they are very complicated and they're not practical. They're only of theoretical interest. This is why being in place and stable makes quicksort a very good candidate. On the other hand, the downside with the quicksort. What happens if you choose not very good pivot elements? What happens in the worst case? So let me give you an array. Okay, so let's say I would like to sort 1, 2, 3, 4, 5. So this is already sorted, I know, okay? But once you give this to the quicksort algorithm, what it will do is it will choose the first element as the pivot element and put the smaller elements to the left and greater elements to the right. But this will not be splitting my sequence. This is just decreasing my sequence, just one element, which means there will be nothing on the left partition. So 1 is here and 2, 3, 4, 5 here. So that means I will do the same here and same story will happen. You see, I am not creating a tree of log n, but that turns out to be a chain of n levels. So that is why in the worst case, quicksort turns out to be a quadratic algorithm, right? Which is not the case for the merge sort. It has the guarantee, right? To avoid this fact, there are some different perspectives on choosing this pivot element. So to avoid this already sorted sequence input case, people said that, okay, so what I can do is median of 3. I will be just selecting 3 elements from this array randomly, and I will choose the median element. So that might be a good pivot element. Or randomly, I will go and check something. With the randomized quicksort, we call them the randomized quicksort, where the selection of the pivot element is the result of a randomized operation. Then you can prove that the expected, again, we cannot say the worst case, but the expected time complexity of quicksort becomes n log n. So in terms of the master's theorem, so the quicksort is no different than the
merge sort, assuming that the pivot element splits the input into two equal partitions. Okay. What else? So there are actually many elements of divide and conquer, but I strongly suggest you to study the finding the maximal subarray given an array of elements, array of integers. I'm trying to find the subarray where the sum of the elements is maximal. Okay, so that's the finding maximal subarray question. So Karatsuba's multiplication is another interesting example. So you would like to multiply two integers. So is there a multiplication method that comes with a reduced cost? So it's Karatsuba's multiplication. Similarly, there is the matrix multiplication. That's a very important thing, and it's n cube in the brute force manner. So with the Strasson's matrix multiplication with divide and conquer, so this is your matrix, you divide it into four partitions and do something. So that's the Strasson's matrix multiplication, a good example for the divide and conquer. And the closest pair, again, this is a nice example for the divide and conquer for your own studies. I guess that is all I would like to tell you about the divide and conquer algorithms. And next lecture, we will continue with the transform and conquer type algorithms. Thank you. Take care.